Hi.
You guys are so silly. Okay, so we're going to record.
No, I thought you were going to say like.
And again, you can find this in recorded lectures, so you'll be able to see it. I'll put today's date in period 5.
Is it facing the other way?
No, it's facing the screen, silly. All right, so everything that we've been talking about fits into your learning goal. At this point, you should be able to define kinetics. So,
is it recording right now?
It is. So, Zach, what is kinetics? That's not the answer.
You're supposed to say hi.
All right. Everybody knows who I am. So as Brandon said, the study of reaction rates and the factors that affect them. And one of the things we've already done is we've learned how to write and solve rate expressions. So the -1 over the coefficient, blah, blah, blah. So you'll see that on your quiz, both writing and solving them. We've talked about the collision theory. Particles have to hit one another with enough force. And what's the second piece of the collision theory? Orientation. They have to be oriented properly. That was the concussion example. And then we're going to take a look at the factors that affect reaction rates. We've talked about concentration. We know how to write the baby rate law, where you're just looking at one reactant. So let's take a look at that now and try and do this. This is a little bit cockeyed. So here is your do now, and let's take about 5 minutes to do it. Give it a shot. Need my calculator. Hey, focus. You're beautiful. Do now, do now, do now.
Video.
Wasn't this classroom?
Nope. All right, so here's your do now. Give it a shot. Go, go, go. You want it a little bigger?
But now, if you're in the video too, then downtime. Oh, they're going to do 2 one day.
Yeah, it's 2.7.
I get it. Is that in our notes?
No. Let me see if I can center it better for you. Nope, that didn't work. We'll just leave it. I'm just trying to make it bigger for you, but you can work off the data table. All right, give it a shot. And then I'm also going to scan whatever I write on today so that the kids who are out have it, and you'll have it as well. lot of you look like you've got it. Some of you are having a little difficulty writing them out, and it just does take a little bit of practice, and you're going to get a lot of that practice today as we go through. Let me show you how to work this one. Some of you weren't sure where to put the N, so I'm going to flip screens. Okay, so what you can see here is that I'm going to do the concentration of the reactant in the second experiment over the first, raised to some power of n. That's going to be equal to the rate of the second experiment, that's the rate at which C is formed in molar per second, over the rate of the first. Now I'm going to be honest, you don't need to write this piece out on your quiz, but from here on I need everything. So if you start here, that's fine, that'll be worth full credit. So then what I did is I plugged in the concentration of A in the second experiment, which is 0.6 molar, that's what's right there, and then the concentration of A in the first experiment. And I put the second experiment over the first simply because the number was larger and fractions sometimes can be a little tedious. Here is the rate of the second over the rate of the first, and I whited this out because in my head I was like, oh, well, that's just 27 over 1, and I wasn't sure you would see it that way, so I went back and rewrote it, units there. The units cancel, so you have 3, which comes from here, 0.6 over 0.2 is 3, to the n power, the order with respect to A, and this over this is 27. So it's not 3 times n, it's 3 to the nth power, so n is 3. That means it's third order with respect to A.
I understand how the molar units are canceled out, but what happens to the seconds on 2.7 times 10 to the negative third?
Well, you've got molar per second over molar per second. So if you have x over x, it's 1. If you have the same units in the numerator and the denominator, they just cancel.
So seconds.
Yeah, because it would be 1 over seconds in each case. And if you have 1 over s divided by 1 over s, that'd be 1 over s times s, which would be 1. So they cancel. So it's as if, let's say you had 2 densities in grams per mil. Density on top, density on the bottom, grams per mil, those would cancel too.
Okay.
Yes?
Yep.
Go ahead.
Can you just explain, like, for the bottom part? I understand that why it says the great decrease.
Oh, I didn't get there yet. I will, I promise. So, do you understand to this point how we got n is 3? Yes? Okay, so then it asks to write a rate law. A rate law has rate is equal to k, some proportionality constant. At this level, I just want you to know that rate laws have k's in them, and only concentrations of reactants. So the concentration of reactant A, now if they gave you a chemical equation and you had a true reactant, let's say nitrogen monoxide, you'd put that in there, and we'll hit that today, raised to the third power, third order with respect to A. Then this is Hannah's question. It says if the concentration of A is halved, so instead of A, I'm putting in a half. And I raise that to the third power, that's 1/8. Anytime you get a number less than 1, the rate will decrease by a factor of the reciprocal. The reciprocal of 1/8 is 8. So it's 1/8 as fast as it was, or 8 times as slow. If you triple the concentration of A, 3 to the third power is 27, and that's what happened here. The rate increases by a factor of 27. Okay? So you have to know that it's the concentrations divided to the power set equal to the divided rates. Now these are relatively straightforward because you have one reactant only. But what we're going to look at is when you have 2, 3, and you could even have 4 reactants. That's a little bit trickier, And if you're very neat with your setup, you'll be extremely successful here. But you've got to understand exponents. So be careful there. 2 to the second is 4. 2 to the third is 8. 2 to the fourth is 16. A lot of kids write 2 to the fourth is 8, and that's a no-no. 2 times 4 is 8, but 2 to the fourth is 16. All right. So that's your do now. And I basically had just rewritten that. So what we're going to look at now is what happens when you have more than one reactant. This is far trickier. Have some patience. It's not that bad, but you've got to really focus and you will be successful. So what we've got here is we've got 3 reactants, A, B, and C. And the rate law is rate is equal to K, proportionality constant, concentration of A raised to the N. The first one's always to the N. Concentration of reactant B raised to the M. We're just going alphabetically backward. Concentration of C to the L. If you had another one, it would be to the K. Some books do A, B, C, but most of the textbooks do not. It says only those reactants that affect the rate appear in the rate law regardless of whether they are reactants. So let's say C wasn't in the rate law. That would mean the order with respect to C is 0, and we'll point that out in a few minutes. That means it doesn't matter what you do to the concentration, there's no effect on the rate. It says N, M, and L are usually small positive integers like we talked about the other day. They can be negative or non-integral. I'm not going there at this level. So it's probably going to be something 0 through 6. If you get 11, please check your math. You probably made an error. N is the order with respect to reactant A. B is the order with respect to reactant B. And L is the order with respect to reactant C. Now the overall reaction order is the sum of those exponents, N plus M plus L. We'll do a few of those. And the key to being successful is you must find the effect by altering one concentration at a time. The other ones have to be held constant. You can't play with 2 at the same time. So you'll be looking for experiments in which 2 reactant concentrations are constant. You want to look at the effect of changing the other concentration on the rate. This will be a little more simple than what I just said, but we'll point it out. So for example, it says write rate law equations for each of the following based on the data provided. Each reaction was carried out at 25 degrees Celsius. This one is all typed out, and we'll walk through it, and then we'll work some out together. Your reactants in the experiment are A and B, and we're running 4 experiments. These are the concentrations of A, unit molar, concentration B, unit molar. This is the initial rate of formation of C. And whatever you're forming has to be a product. Here's its initial rate of formation. And you can see in molar per second the rate at which C formed. Previously, we just took this over this to the end and this over this. But there's something else you have to look at now. You have to hold one reactant constant and look at the effect of the other. So what I do is I just look at the data, and there's no set way of what you do first. It doesn't matter as long as you hold one constant and look at the effect of the other. It says here compare experiments 1 and 3. So if I focus on those 2 lines, what I am seeing is that A is tripling and B is constant from experiments 1 and 3. Doesn't change. So I can look at the effect of tripling A on the rate. Does that make sense? Why do I have to hold this one constant to look at the effect of A?
The rules is,
I didn't catch that. Hannah?
So like see the change in one specific one.
Exactly, to see how one reactant affects the rate. If they're both changing, you won't know what change is causing the effect on the rate. So we're going to look at the effect of A, we're going to hold B constant, and then we're going to do it just like we did in the do now. This over this to the n is equal to this over this, and that's what's shown, written out here. It like jumped. It was a poltergeist. So you've got 0.3 over 0.1 to the n, this over this. This is 3 to the n equals 1. So 0 order with respect to A. Doesn't matter what you do to the concentration of A, it has no effect on the rate. Now if that happens, you don't ever have to hold A constant because it's not affecting the rate. But we'll hold it constant here just to show. I'll show you when it really wouldn't matter. All right, now we want to look at the effect of changing B, and let's hold A constant because it's a good habit to get into. So where is A constant? 2 and 3. It doesn't change. And you can see B from experiment 3 to 2 triples. So I'm going to do this over this to the m is equal to this over this, and that's what's shown here. Again, I like to put the big number on top because then I don't have to deal with fractions. If you want to do fractions, that's fine, you can. So you get 3 to the m, and then 9 over 3. If you have the same exponent here in 10 to the power, then this essentially cancels. So 9 over 3, 3m to the 3, m is 1, first order with respect to B. So when we go to the rate law, we have rate is equal to K, A to the 0, B to the first, and then this piece right here is 1, so we just write rate is equal to K times the concentration of B. The overall order is the sum of the exponents. We only have an imaginary 1 here, so the overall order is 1. Okay? It's nice to have a problem all typed out for you, but it's really more helpful if we work through a problem where there's nothing there except what we need to do. So we're going to take a look now at numbers 2, number 3, and then we'll do the other one.
Dr. Katie,
Yep.
does it matter which experiments you compare? For example, in the first one, you had experiments 1 and 3, and then you used 2 and 3. Could you compare 1 and 4 or 1 and 2? Or do you have to compare 1 and 3?
What do you think?
Well, not sure.
Okay.
I mean, you have to keep one constant, but it doesn't matter what you keep constant.
Well, what would you like to use then? If you were looking at the effect of A, where are the only 2 experiments where B is constant?
1 and 3.
1 and 3. And if you want to hold A constant, which in this case isn't necessary because it's 0 order, what are the only 2 experiments where A is constant?
2 and 3.
So it does matter. Otherwise, and that was Hannah's answer right there, otherwise you're not really looking at the effect of that concentration on the rate. Okay? And you'll see it right here. So we're going to work, I just reprinted this so it would be a little bit easier. Can you see in the back? That's good? Yes, yes? And there are some good seats available. We've got Lexi's seat, Gabby's moved, Jordan's seat. So for those of you with nosebleed territory, maybe you want to move forward. All right. let's take a look. And Grant, you're going to help me answer that question, which is an excellent one, in a little more detail. Okay?
Mhm.
What do you want to look at first? And there's no correct answer. The effect of nitrogen monoxide or the effect of chlorine gas?
The effect of chlorine gas.
Okay. So if we're going to look at the effect of the concentration of chlorine gas on the rate, what must we do?
Compare experiments 1 and 3.
1 and 3. How come?
Because the molar is equivalent between 1 and 3 for the initial chlorine gas.
Okay, but if we want to look at the effect of chlorine gas on the rate, we want to look at the effect of altering chlorine on the rate. So do we want to hold it constant or the other one?
The other one.
The other one. Okay, so we need chlorine gas concentration to change to look at the effect on the rate, otherwise we're not looking at the effect of anything. So we have to hold nitrogen monoxide constant right here to figure out the effect of chlorine. And what I like to do, and I think it will be helpful to you as well, if you simply write 1 and 2, that tells me that you're looking at experiments 1 and 2 right off the bat, and then I know where your focus is. So you're holding nitrogen monoxide constant, and now what you're going to do is you've got 0.0510 molar over 0.0255 molar, and that's to the M, because it's the second substance in the equation. And now you're going to do the rate of the second over the rate of the first. And that's going to be 2 to the M is equal to 2. So M is equal to 1. So it's first order with respect to chlorine. And sometimes I'll put a 1 here because it's easier to write the rate law at the end. That's up to you. Yes, so far? Okay. Now we're going to look at the effect of concentration of nitrogen monoxide on the rate. So what experiments do we need to look at?
1, 3.
Why?
Because the value changes, the value for chlorine gas stays the same.
Yes, the concentration for nitrogen monoxide changes, but chlorine's held constant, and that allows us to look at the effect of nitrogen monoxide on the rate. So we're going to look at experiments 1 and 3. So I really like writing that in. I think it's very helpful. And now I've got 0.0250 molar over 0.0125 molar to the N, because it's the first reactant, over 9.08 times 10 to the negative 5 molar per second over 2.27 times 10 to the negative 5 molar per second, and that's 2 to the N is equal to 4. So what's N? 2. And now we can write our rate law. Sometimes I'll put a 2 right there because it's just easier to grab everything at the end. And a rate law is rate is equal to K nitrogen monoxide squared chlorine gas to the first, and you don't have to write a 1. Not that bad. You just have to be systematic in your approach. Questions on the rate law?
So all you're doing is comparing the second one, the first one, and the third one, the first one?
And you understand why, correct?
Because they have changed it.
One has to change while the other's held constant, and then vice versa.
So like if chlorine had like it was the M equaled like 2, then after the chlorine you put like a 2 there.
Uh-huh. All right, let's try one harder one, ever so slightly harder, and this is pretty much as hard as it can get. All right, so why does it look harder right away?
Four.
Because you have 4 experiments and 3 reactants. You've got a lot of data to look at. So if you're looking at the effect of one thing, you have got to hold 2 of them constant. Now, one thing I will tell you for this year only is if you see that something cannot be held constant, figure out what its order is first. And more than likely, especially for this year, the order with respect to that substance will be 0. But we've got to prove it first. Because if it's 0, does it matter what you do to its concentration? No, it doesn't affect the rate. But let's take a look. So because this one can never be held constant, I've got to get the effect of concentration B first. And in order to do that, I have to hold both A and C constant. A has to be constant, C has to be constant. They don't have to be constant to each other. Where is A constant and C constant? 1 and 2. Because in experiment 1 and 2 for A, the A is constant, the C is constant. I can look at the effect of doubling B. I can see the rates unchanged. Right away I know that's 0 order. We'll prove it. So in experiments 1 and 2, what we've got is 0.40 molar. You don't have to put that in brackets anymore. 0.20 molar raised to the M for reactant 2 is equal to 3.0 times 10 to the negative 5 molar per second over 3.0 times 10 to the negative 5 molar per second. 2 to the M is equal to 1. N is equal to 0. So that means it's 0 order with respect to B.
It's per minute.
Huh?
Does it matter?
It-
You wrote M over A.
What?
The
Oh, it's
it's what, minutes, not seconds. Does that matter?
It matters only because I was sloppy. Not going to change anything though, but thank you. I'll fix it.
Everyone's like,
Yeah, so this is a slower reaction if it's measured in minutes. Couldn't understand what you're talking about. All right. Now, okay, that's really important to know. If anything is zero order, you don't have to deal with it for the rest of the time, because altering its concentration clearly has no effect on the reaction rate. So what would you like to look at next? Effect of what? Okay. So what do I have to hold constant, and what do we have to do to A? Do you want A to change? Yes. We want A to change, and C has to be constant. So C is constant in experiments 2 and 3. A changes, and there's D.
Okay.
Yes.
When something has when the exponent of something is equal to 0, which is 0 to the first order or something like that.
No. If an N, an M, or an L is 0, that means the order with respect to that reactant is 0, and the interpretation is it doesn't matter what you do to the concentration, there'll be no effect on the rate.
So you ignore that when you're looking at the next.
Yes, because we've shown right here that doubling concentration of B had no effect on the rate. So it doesn't matter what you do to B, there's no effect on the rate, so we don't have to consider it as we try and determine the rate law. Okay? All right, so with A, we're going to have 0.20 molar, 0.10 molar for experiments 3 and 2 respectively to the N, because it's the first reactant. And then we're going to have 2.4 times 10 to the negative 4 molar per minute. That's a sloppy minute. 3.0 times 10 to the negative 5 molar per minute. So that's 2 to the N. 24 over 3 is 8. What's N? 3. So the order with respect to A is 3. And like I said, if you're just neat with your setup, you're going to be very successful with these types of problems. Okay, and then the last thing we want is the effect of C. So we don't care about B because the order is 0. What do I hold constant? What must change? Okay, so where is A constant and C changes? 3 and 4. And please note, I didn't write 2 and 3 here initially. I just wrote it in, so add that so you've got it. Some of you probably put it in. So now with experiments 3 and 4, A is constant. You can see we're quadrupling C. So we have 0.80 molar over 0.20 molar. To the L. And that's 3.84 times 10 to the negative 3 molar per minute over 2.4 times 10 to the negative 4 molar per minute. And that's 4 to the L. Probably 16, right? Yep.
Why do you use L?
It just goes backward in the alphabet, so it's N, M, L, then K, then J, and then it would be so difficult you wouldn't want to know what came next. I'll tell you why, because when you do, remember the generic equation I showed you where you had like reactant A and reactant B making C and D, and you had lowercase letters before for the coefficients? Are you with me or no? Okay, I'll illustrate that in a minute, okay? So now we've got, what is L equal to? No, silly, 2. Careful with the exponents.
Can you push it up so you can see?
Yeah. No.
Would you write for?
That's not me.
Is it FLB?
Okay.
Guys, just turn your phones off, silly. Yes.
For A, you wrote and then you wrote B, you put 0. Because why'd you cancel out? Like in the chart, you canceled
Here,
Yeah.
why did I cancel this?
Yeah.
Because if something's 0 order, it doesn't matter what you do to the concentration, there's no effect on the rate. So I don't have to hold B constant because it doesn't affect the rate, making the problem a little more manageable. Now we've got all the pieces of the puzzle. We have rate is equal to K, A to the 3rd, B is to the 0, so I'll put it in here and then I'll take it out. C squared, or you would just say rate is equal to K, A to the 3rd, C to the 2nd. So if something's not included in the rate law and it's a reactant, it's 0 order. What would the overall order be here? 5. How'd you get that? You add the exponents. Okay? It's tricky. It takes a lot of practice.
This side or left hand?
What can't you see?
Whatever's on C.
Here? All right.
When you want the effect of something, you have to find the change of that, and then something that goes constant.
Correct. And usually you have to hold everything else constant unless something's 0 order. And you'll see in the next one's much, much harder than anything I'd give you. I think the AC stopped working.
I know.
If you're not looking for the effect of something, like say for the effect of A, you have to find where A changes.
Correct. Otherwise, you're not looking at the effect of it. If it remains constant, it's not doing anything to the rate. So if you ever divide 2 concentrations and you get 1, you messed up. So 1 to some power, you messed up. All right. Let's do a little bit of interpretation, and then I'm going to leave you to try and do 4. I will do 4 out so that you can see it. And then you'll have the remainder of the period to practice, practice, practice. This takes practice, okay? So in terms of the interpretation, we did this with simple rate laws. This is a little more complicated, but you're good at math and you're going to be very strong here as well. All right. In regard to the interpretation, it says analysis of the effect of a change in concentration using rate law. Determine the effect of the rate in each of the following and determine overall order. So at looking at these, maybe I will, guys, I know it's very warm in here. If you just sit quietly, it'll be better. If you jump around, it will be far worse. No, don't. Silly. You can't sit in the freezer. That's silly.
What a bit.
Flip side.
Are you so adamant?
It is quite warm in here.
Because the AC is working out here.
Okay.
You want me to put those things?
Yes, please.
I swear to God, we have to do this for the rest of the year.
I'm actually not that hot.
She's freaking
How far open do you want me to make it?
all the way.
All the way.
You heard the bosses.
23.
All right.
40.
Let's take a look. Yeah, that'll keep you honest. Alrighty. Let's look at the first problem. Let's do overall order here. All right. Raise your hand. Give me overall order of the first rate law.
4.
4 is correct. 2 plus 1 plus 1 is 4. All right, overall order for the second. 2 plus 1 plus 3 is 6. How about this guy?
7.
2 plus 3 plus 1 is? No, it's not 7, Goofy. Ha ha ha, you're so funny. Questions on overall order. On the quiz, I'll give you a rate law and I'll ask for the overall order. If I asked, look at this first problem. If I asked for the order with respect to A, you would write 2. If I asked for the order with respect to B, you would write 1. 1. If it's not there, it's to the first power. If there's no exponent, it's to the first power. If the substance isn't in the rate law and it's a reactant, it's to the 0. The order with respect to C is 1. All right, let's interpret. It says A is doubled, so we're going to put a 2 here, squared, and B is halved.
Wait.
A is doubled, we put a 2 here, B is halved. What's 2 squared? Divided by 2 is? 2. So the rate increases by a factor of 2, or the rate doubles. Okay. It says A is doubled. What am I going to substitute A with? 2 to the third. B is halved. And C is tripled. Now just be careful. 2 to the third is 8 times a half times 9. So you have 4 times 9 is 36. The rate increases by a factor of 36, or it's 36 times as fast. Try number 3. Quartered. So what would you put in for A? B is doubled. C is quartered. 1/4 squared is times 8 times a quarter. I would probably do this and get 1/8. So the rate decreases by a factor of 8, the reciprocal. If you got an answer out at 3/8, the rate would decrease by a factor of 8/3. So make sure that the factor here is the reciprocal when it decreases. Okay? All right. I would like you to, at this point, you can do through number 17, but we all know that's a little too much for today. But I'll tell you what, if you do that crazy problem and you do through number 10, I think you'll be in really good shape. And tomorrow, we will just practice. Practice, practice, practice. Tomorrow, I'll come up with some fun problems. All right? I will do number 4 on my sheet. You will do number 4. Once you've checked your answer, you can go to the side tables. And like I said, you can do through 17. But if you go through, actually, you can do through 18. But if you go through 10 today, I think that would be really good. Questions?